So electricity is pretty cool, and I'm pretty confident I can teach you more about it just using water and bacon in this video. And if you want to learn more about this topic and other cool university and life hacky kind of things, just subscribe to my channel while you're here. So one time or another, many of us have wondered how electricity works. Most people have just maybe accepted over time that it's like magic, and what about the daily lives? And if it seems like magic to you, then welcome to my school of witchcraft and wizardry. Let me teach you some spells. Maybe that was a bit much. So to wield electrical energy, we're going to need a good foundation of understanding of what it is. And that's what this series intends to address. So electricity is a part of the fundamental forces in the universe that permeate pretty much all parts of existence. And by using its energy, we humans have molded our world to fit our wants and needs. So this will be the first episode where we're just going to explore some of the fundamentals, give you a decent understanding of how it works. In the following videos, we're going to expand on this foundation that we're going to set today. And so, yeah, let's just dive into it. And we're going to start just by looking at where you use electricity in your daily life. Electricity makes things turn on, makes things move, glow. It can heat things up, cool things down. You probably have something in your pocket right now that is run on electricity. People have cars now that run on electricity, and out of all these things, we really only use two different effects that it has as it flows to our advantage. First thing we take advantage of is it generates heat, and we use this in space heaters, light bulbs. We use it in our block heaters in our car, and in many other places. And anytime current flows through a circuit, heat will be generated. And hang on to that thought, because I'm going to come back to that in just a little bit. So the second effect that comes with the flow of electricity is going to be electromagnetism. And now in my previous video, I've demonstrated different ways that you can use some electromagnetism to make some cool things happen. And I'm going to do more in a future video. For now, just note that anytime current flows, along with creating heat, we also generate an electromagnetic field. And we can make that field stronger by winding it into a coil. And we take advantage of that in places like in motors, solenoids, power transformers, and even transistors will use the electromagnetic field effect to turn on and off. And again, I'll explain that in future videos because there's way too much to cover there in this video. So to start our quest in mastering the universe, I need to give you a sacred key of understanding for electrical basics, and that's going to be found in Ohm's law. So this fabled triangle, it'll help us unlock the secrets we desire. The triangle consists of three letters: V for voltage, A for amperage, and R for resistance. So this triangle is a clever way of helping us define the relationship between these three, as well as containing another secret which we will unlock later in this video. Starting with voltage, we define voltage as the electrical potential between 2 points, or the pressure between 2 points in a circuit. So, for example, your 12-volt battery in your car has a positive and negative terminal, and between the two there's 12 volts. So you can connect a bulb or a motor, which we would refer to as a load in the circuit. So the energy will flow from one side of the battery to the other, slowly equalizing that potential energy until there isn't any more and the battery is dead. But what does voltage mean? What does that 12 volts refer to? So to help explain it, I want you to think about voltage like you do water pressure, just for this example for a little bit. So pressure is generally going to be defined as the available difference in energy from one point to another. Pressure inside of a fire hydrant, for example, is going to be considerably higher than the pressure in the atmosphere around you. I mean, that's why if you backed your car into a fire hydrant, water would spray everywhere, because the pressure wants to equalize, right? Higher the pressure, the more ability it has to equalize itself. And we can demonstrate this with electricity with something like a Tesla coil or a high voltage arc generator like the one here that I made. So if the pressure, electrical pressure, gets high enough, so the voltage, the difference in voltage is high enough between these 2 points, then the resistance in the air is going to be low enough for that arc to jump, because it has enough pressure to push through the air and create an arc that can be sustained. So I will demonstrate that here. It's really fun to play with. So much like water, the higher the pressure, the further it will go, or the more push it'll have behind it. Now, the high voltage can be dangerous, and many people die each year from voltages that exceed 1,000 volts. But a static shock can actually be in excess of 10,000 volts. So why doesn't it kill you? And that brings me to the next letter on our triangle, amperage, or the flow of current. So if voltage is the pressure pushing the water, current would be the amount flowing. So to put this in perspective, I'm going to look at a water gun versus a river. Now, I asked my kids if they could spray me in the face with a water gun, and they were more than happy to oblige. So I got them to be about 10 feet away and spray me. So the water pressure in the gun has to be fairly considerable to be able to go all the way and hit me from 10 feet away. But when the water hits me, it just bounces off and it does nothing. Now, if we replace the water from that gun with the water from a river, and I don't just mean a little bit, I mean the actual entirety of a river, it'd be a different story. I would be dead and gone, and the surrounding area around me would also be completely gone. So what is the difference between the two? The water from the water gun and the water from the river, they move at about the same speed. So why would the river kill me and the water gun just bounce off? And I'm sure it's actually fairly obvious. The difference is the volume of the water flowing. So the river and the water from the water gun have the same amount of push or pressure per millimeter of water, and they'll move at the same speed, but the amount of millimeters being pushed it's vastly different. The amount of energy carried at any given moment is dependent upon both of the factors, the force of the pressure and the volume flowing. And with electricity, our voltage would be our pressure, and our amperage would be our volume, or the current flow would be the amount flowing. So the water gun is like static shock. It's got a lot of pressure to be able to get to you, but not enough current to actually be able to hurt you. And our river would be more like a lightning bolt, where we have quite a lot of pressure and a lot of current traveling with it. So it's, unfortunately, if you got hit by it, it probably would kill you. But electricity is not like water in all circumstances. So the more current that flows through an electric circuit, the more heat is generated. So anyone that works with electricity needs to be able to make sure that they're using the correct components, wire size, and temperature control systems for the application, or they'll risk starting a fire. And that actually happened to me once. I made a prototype lithium-ion battery pack for an electric boat I was building, and the wires inside the pack were a little bit too small, and it actually ended up catching fire in the middle of the lake. Thankfully, I had a circuit protection device, which is a fuse located inside of that battery pack that blew to prevent it from catching fire. And this is why we use fuses, because a fuse will blow under the situation where the current draw exceeds the value that it's rated for. Each fuse has a rating. Your house has fuses, your car has fuses, and every electrical device you've ever used that's designed by proper engineer is going to include some kind of overcurrent protection. That's standard. So the amount of current flow isn't only based on the amount of push that it has behind it. It's also going to be based on the resistance that it has to overcome to get to where it wants to go. And that brings us to our final letter on the triangle, which is R for resistance. So resistance will be defined as anything that will impede the flow of current in an electrical circuit. The unit of measurement we'll use is called ohms. Same guy that came up with the triangle called the resistance unit after himself. So all circuits have resistance, all wires have resistance, all components, materials, gases, even you have electrical resistance. Yes, you do. It's fairly high, not enough for a 12-volt battery to really do any damage unless it gets under your skin, but it is enough that a higher voltage could actually push enough current through you to be able to kill you. So that's where it gets dangerous. So again, using water to demonstrate the flow of current through a circuit that has resistance, I built this little contraption. It's got a pump inside the little reservoir here, which builds the pressure, which is going to send the water through the tube up to this valve. Now with this valve, I can vary the amount of restriction just by turning that valve one way or the other. So I can essentially vary the resistance, and we'll watch as the current out changes, the current flow changes. And I'm going to note a couple really key aspects of current flow in relation to resistance once I get this going. So just pay attention here. So I've got the valve wide open. So this is the lowest amount of resistance that we're going to have. So that would mean that it's the highest amount of flow. So you can see that the amount of water that's coming out and returning back to the source. So as I change the amount of resistance, so I'll increase the resistance, you can see the flow will decrease. Now we got just a little dribble there of water, right? So the current flow through the circuit, from the beginning all the way through to the end of the circuit, it's the same. The pressure isn't the same throughout the circuit. So the pressure will be the same up until the restriction. After the restriction, the pressure will just drop down to essentially zero. There's really no more pressure here on this side. So the same is true for electrical circuits. Our voltage will be consistent from the source all the way up until our load. And once we meet our load or our resistance in the circuit, then our voltage or our pressure is going to drop after the restriction, assuming there isn't any more restriction or resistance on the other side. So again, this is very awesome way to just demonstrate how a circuit operates, and this is true for pretty much any circuit in existence. So I will cut that off completely. So now our resistance is infinite. The amount of pressure, it can't overcome the resistance, and no more current can flow out until I decrease that resistance, and current can flow once again. And as I say, it's the same with electrical circuit. So if this was a circuit, and let's pretend this is like a light bulb or something, so to divide this into the three different parts, we have our source, which is where the current comes from and the pressure is built on, and then the restriction here, or the load, and that's the thing that we're going to have to try to make work happen. So like our motor, light bulb, whatever it's going to be, that's going to restrict the amount of current flow. And then we're going to have our path back to the negative terminal, or we're going to call this the ground portion of the electrical circuit. So now what do you think would happen if I got rid of that restriction? So in a electric circuit, when we have a restriction that gets bypassed or a restriction that gets eliminated and there's still a path for the flow to ground, we would essentially just call that a short. So when we remove the resistance from a circuit and short it out, the source is going to just output however much current it's allowed to output. There's nothing restricting it anymore. So I'm going to cut this, and essentially what I'm going to do is I'm just making so there is no more restriction in here. So the pump can just feel free to spray as much water as it wants to everywhere. Now this is going to be the same as a short circuit in an electrical circuit, because once we eliminate that restriction and there's nothing stopping the amount of flow of current from being output anymore, then it's just going to output however much current it can. That's how it works. And I mean, that's why we use fuses, but you know. Yeah, short circuit. Just turn this off. So we're getting really close to setting up the thermal camera and cooking some bacon. But first, I wanted to just finish up with our triangle up in the corner here. So the big secret hidden in Ohm's law is three little math equations. And these math equations are there to kind of help us figure out exactly what's required for a circuit to operate if we know some of the other values. And I'll explain it like this. If we want to figure out our voltage, we can figure it out just by simply taking our amps and timesing it by our resistance. If we want to know our amps, we'll take our voltage and divide it by our resistance. And if we want to know our resistance, we'll take our voltage and divide it by our amperage. So just as an example for that, if I had a circuit with a 10 ohm resistance and it drew 1.2 amps, I know that my voltage must be 12 volts. Now, while this is handy in practical application when we're designing building circuits and diagnosing, fundamentally, it shows that each of these values cannot change independently. Voltage, amperage, and resistance have a direct and immediate effect on each other, and our ability to use electricity to our advantage is built on this fundamental relationship. Okay, so now for my plans with the bacon. So I want to demonstrate current flow generating heat. So I'm going to try to cook bacon with electricity. Now, I want to generate heat inside the bacon. I know typically when you cook with electricity, you think like a stovetop, which heats up an element, you put your pan on, and that makes the pan hot. I want to make the bacon directly hot with electricity. I don't want to use a pan. So I'm going to be trying two different electric cooking methods, and we're going to be observing the heat generated from the flow of the electricity through the bacon with our thermal camera. So the first cooking method we're going to use is going to be with high voltage, low current. And this will be with my high voltage arc generator. The second method we're going to be using is using high current, low voltage. And that's going to be with an arc welder. So I have a feeling that these results are going to be shocking. Absolutely just electrifying. I'm sorry for my puns. I'm just so positively charged about this. I just had no negativity left in me. Ow. One thing I'm really curious about trying to learn here is if I put the high voltage arc to the bacon, will it actually cook the bacon along the entire path that the current is flowing through the bacon? Or is it only going to cook the bacon where that high voltage circuit is connected to it? Now I got the bacon set up in the shock zone, and another thing I'm going to have set up this time is a little thermal camera I have. Now this thermal camera is going to be watching as we pass the high voltage arc into the bacon, and it's going to show us hopefully exactly where the heat is being generated in the bacon, so we can decide how best to thoroughly cook this so I can make sure I can eat it at the end of this. So you can see in my thermal camera here that here's the bacon, and if I put my hand in there, you can see the temperature of things that radiate heat. So right now the bacon is the same temperature as all the background environment behind the bacon, and so the camera kind of just auto adapts. Now my body is a fair bit warmer than the background is, so that's why when I bring my hand in there, it immediately picks it up and it gives you that contrast. Woo. I don't think I'm actually going to be able to cook this with the arc generator because every time I try, I keep getting these little holes. That's all it does. It isn't actually cooking the bacon. So previously in this video, I mentioned that heat should be generated along the path of the resistance. And looking at that thermal camera footage, you may think that I lied to you, as the heat only seems to be generated where the high voltage arc is actually contacting the bacon. But remember, with the high voltage arc, we have two different medians it actually has to travel through. The first is the air that gets superheated when the high voltage arc travels through it. And after all, that superheated air is actually what you're seeing. That is the arc. That's what's releasing the light. So, and this is the heat. It's actually burning the holes in the bacon. That high voltage arc creates a hot spot in the air right above the bacon, and it just burns. It instantly fries the area that it's jumping to. So remember what I said when it comes to resistance. Anytime current is flowing, heat is generated. And that high voltage arc has very little current behind it. It's high voltage, low current. So there won't be a noticeable amount of heat generated along the path of the current flow through the bacon because there's not a lot of current through it. So the current wasn't really enough to cook the bacon with the high voltage arc generator. So now let's try the arc welder. To cook the bacon with the arc welder, I have to make like a platform that has the contact points pretty close together, because the closer they are together, the quicker it'll cook. So I got my science bacon. In a house with kids, you got to make sure that you label things appropriately. Anything in the fridge typically labeled with science anything is usually safe. People won't usually touch it. Now getting the thermal camera set up here. And we're going to turn the arc welder on. The thermal camera rolling. Arc welder's on. Now there really shouldn't be any current flowing right now because nothing's contacting anything. So good. Now what you have to do is put some of this bacon on there. See, it's cold in the thermal camera. Oh, cool. See, it's red in the middle. So that's going to be areas where it's heating up. I'm hearing something happening over there. Something's definitely happening. Cool. So that's just cooking with electricity. That's all it's using to cook it. You see our thermal camera So we have an areas across where it's getting nice and hot. And we can also see over here, it's still cold. And that's because there's no current actually flowing through that spot there. Most of the heat is being generated across where the current is flowing. Oh, so cool. So one thing I do want to mention about this is that bacon right now, it's not cooking because the surface it's on is hot. It's cooking because there's electrical current flowing through it, and whenever current flows, heat is generated. So I get both shots in there. So the heat's kind of building mostly on this piece of meat and then coming around. So it looks like it's actually cooking it fairly thoroughly now. So now I just wanted to create one final version of the bacon cooker that connects to the arc welder. Now the reason for using so many little wires is just so there's more paths for the current to flow through. I want to be able to drop the piece of bacon on there and just have it start cooking right away, nice and quick and nice and thoroughly. And this last check I'm doing with my multimeter is just testing to make sure that none of the wires from one side are touching the wires on the other. And that is it. With that, it looks like that this design is the winner. Higher current is definitely the way to go if you want to ever cook bacon with electricity. That's it for learning the basic electrical fundamentals with water and bacon. Now the next video we're going to be going a little bit more in depth on these fundamentals, and we're going to be expanding into electromagnetism. We're going to be doing some cool stuff with waves, with induction, and lots of other cool things. So please like, subscribe, ring the bell for notifications to be there when that video comes out. And thank you for watching this and supporting my channel. So have a good one, guys. Stay creative.